Alright, so today I'm going to be explaining this important paper with the title Provably Powerful Graph Networks. This NeurIPS paper in 2019 by Israel. So WL graph isomorphism test was used to measure the expressive power of graph neural networks. It was shown that the popular message passing GNN cannot distinguish graphs that are indistinguishable by 1WL test. Unfortunately, many simple instances of graphs are indistinguishable by 1WL test. In search for more expressive graph learning models, we build upon the recent k-order invariant and equivariant graph neural networks and present two results. First, we show that the k-order networks can distinguish between non-isomorphic graphs as good as the KWL test, which are provably stronger than the 1WL test. This makes these models strictly stronger than message passing models. Unfortunately, the higher expressiveness of these models comes with the computational cost of processing high-order tensors. Second, setting our goal at building a provably stronger, simpler, and scalable model, we show that a reduced second-order network containing just scaled identity operator augmented with a single quadratic operation has a provable 3WL expressive power. Differently put, we suggest a simple model that interleaves application of standard multi-layer perceptron applied to the feature dimension and matrix multiplication. Currently, the most powerful methods for deep learning graphs are message passing neural networks, but they have limited expressive power. So here you see the two graphs not distinguished by 1WL. So the previous video I showed you this paper Maron from Israel that they have suggested a family of permutation invariant deep neural network models for graphs. Their main idea is to construct networks by concatenating maximal expressive linear equivariant layers. So a k-order invariant graph is a composition of these equivariant linear layers. And the sigma here you see is an entry-wise, it's a nonlinear activation. So the invariance of this F is achieved by construction, by propagating G through the layers using definition of equivariance and invariance. So we will present colors as vectors. We will use tensor C to encode color per k tuple, that is the color of the tuple I, which is a vector C sub I. And the key technical part is the way we encode the multisets. Since colors are represented as vectors, n tuple of colors is represented by matrix. Thinking about X as multiset forces us to be indifferent to the order of rows. That is, the color representing G.X should be the same as the color representing X. One possible approach is to perform some sort to the rows of X. We suggest to encode a multiset using a set of S sub n invariant functions called power sum multisymmetric polynomials. The PMP are the multivariate analog to more widely known power sum symmetric polynomials. A key property of that is that the finite subset generates the ring of multisymmetric polynomials. So given two colored tensors C, the tensor that represents for each k tuple is simply C and C prime. So they proved that k-order graph neural networks are as powerful as KWL. And this is the main idea, main architecture of this model, this network. So you see there, they just use different MLPs and they put it differently. And the model is invariant. So F is MHBD and B1, BD, you see here, B1 to BD are blocks with the following structure. That we get X is the input tensor to the block. We apply 3 MLPs to input tensor. This means applying MLP to each feature of input tensor independently. Second, matrix multiplication is performed between matching features. And that's it. This is the architecture. So they did comparison with different models. For example, QM9 dataset, because this has a target for regression, so they compare it with their models. Or they also did for graph classification. These benchmark for graph classification like MuTalk and proteins. So for example, they compared diffpool, which is a hierarchical graph pooling methods, with their methods, hours 1, 2, 3.